Hello, and welcome to Fun with Chemistry and Gas Pressure. We are going to talk about gases today. I haven't done much with solids, liquids, and gases with you because that's something I think you've probably done over and over and over again. We all know that a solid has particles that are touching each other, and those particles are moving, but they're not moving very much. They just kind of wiggle back and forth. All right? They hold their shape. A liquid, on the other hand, those particles are still touching each other. They're still maybe going like this, but they got a little bit more energy, so they can roll over each other. They don't hold their shape. They're moving enough that they vibrate around and move. So they have a little bit more energy than the solid, but not a whole lot. All right, if the arrow represents energy. A gas, on the other hand, has enough energy that it basically escapes and takes the shape of the container. Okay, instead of being lined up at the bottom like a solid or a liquid, it can take up the whole space. And that's what we're getting ready to talk about. Gas pressure is the pressure exerted by gas molecules as they strike surfaces. So here the gas molecule hits the surface, it's going to exert pressure. All right, we calculated pressure, for those of you who've done physics, by taking force divided by area. Now, you all have experienced pressure every day. You live at the bottom of an ocean of air, and that air is pushing down with 14 pounds of force for every 1 square inch, and a square inch would be about that big. Okay? Can you see that? There's about a square inch. So that square inch is that pressure's pushing down, and you are used to that. Now, the weather is not quite that simple. When you look at a weather map, you have highs and you have lows. The highs are areas where there's more air pushing down on you. All right, so you have more than 14 pounds per square inch pushing. The lows, the air tends to be rising, and the air is not pushing as much on you. You're not rising, but there's less air to push on you. So you feel less pressure. It's going to be less than 14 pounds per square inch. This is why people start talking about, oh my gosh, we must have a weather change coming because I've got a migraine, or my knee hurts, or my bones hurt, or what have you. There is a lot of thought that air pressure can affect different parts of our body. You may have gone up in an airplane, and when you go up in the airplane, or you go to the top of the roller coaster, or you go into the mountains, if you have less air pushing on your eardrum is going to be pushed in. All right, and that can hurt. Now, you have this lovely eustachian tube that's attached to the back of your throat. This is why chewing gum helps to relieve air pressure. Swallowing. A lot of times if you have a baby that's going to be on an airplane, they tell you to have the baby take a bottle while you're taking off and landing, because just the act of sucking can help keep the ears open. The reverse would be if you had higher pressure, and then the eardrum will push in the other direction, just as painful. If you have ever gone, had somebody throw stuff for you in a pool, and you go dive down to the bottom of the pool to get it, you get pressure on the inside of your ears, and again, that is caused by, not only do you have ocean of air on you, but now you have a pool full of water pushing on you. All right. Pressure is the result of molecules colliding with the side of a container. All right, the gas particles, the things that affect gas pressure, the number of particles that you have, N for number, and it really means how many moles you have. The volume, we're going to use liters for volumes. And then the third piece, average speed, refers to how fast the particles are moving. And we use temperature to measure that kinetic energy. So temperature, the three things outside of pressure that affect the pressure are number of particles, the volume, and the temperature of gases. The total pressure of a gas depends on several factors, including concentration. The higher the concentration, the greater the pressure. Well, that makes sense. If you got more people in a room, you're going to have more pressure. Think about if you, well, I don't have a good example for that. If you have fewer particles, those particles aren't going to come in contact very often with the sides of the container. Think about if we cleared the room out and had no desks in here, and we had you guys all up and just start walking around everywhere, just bouncing off of walls, whatever. And then we brought Bird Camp's class in from next door and had them walk around with you. More people is going to mean more collisions, either with each other or more collisions with the sides of the room. All right? And that is what we're talking about when we talk about concentration. Now, if you change this, if we take this room and you're in my room walking around and we suddenly cut it in half, you're all going to be closer together, aren't you? That's a higher concentration. So you can change concentration either by putting more particles or by changing the volume so the volume gets smaller. Okay, and here's a drawing talking about particle density, which again is concentration. Of course, density is equal to mass divided by volume, and in this case, the mass is related to the number of particles. We need to know the moles and the molar mass. So for pressure and density, we'll be talking about number of particles and volume. And we just did the ear one. Let's talk about a barometer. A barometer is something they talk about on the news. Again, this is something you're probably very familiar with. Old-fashioned barometers used to be tubes of mercury, and I can remember seeing one in the chemistry lab. And it was in the corner, and the tube was probably smaller than my pen, and it had a bowl of mercury at the bottom. And as the pressure increases, more air pushing down, the mercury would go up. And as the pressure decreases, if we have less pressure, the mercury would go back down. Okay? Now, I have a little video to show you. If I can get there.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seems to hold true in everyday life, we've seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, The idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened, and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Alright, so you saw that little video about a barometer. Basically what you have is, again, that barometer is a mercury barometer in a pool. Nowadays we don't have a mercury barometer because of safety concerns, because of poisoning, but they have what they call aneroid barometers, which have a dial on them, and as air pressure pushes on the aneroid barometer, the dial will increase, and as it pushes less, the dial will decrease. All right, here are some different pressure units that you might come across. At sea level, we have 1001 323 pascals. That is also, we probably would use 101.3 kilopascals instead of pascals. 14.7 pounds per square inch. We already talked about that. Torr, and a torr is the same as a millimeter of mercury. All right, and this is one you'll see because the book likes this, so you're going to see this in the Mastering Chemistry problems. Inches we use in America, of course, but interestingly enough, if you watch the Weather Channel during hurricane season, they'll report the pressure in millibars instead of millimeters, and they are slightly different. They're not the same. All right, and then we can also use a called atmospheres. So the ones you're going to see in class, 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals. Those are the three that you'll come across in class. All right, that is all we have on our notes for gases, the introduction for gases. Thank you very much.